Let's talk about spatial queries. When we talk about spatial relationships, that's what spatial queries are based off of. How things interact with one another, relationships between their positions, and the different things of how the various features relate to one another. That's what drives the possibilities of the different queries. And so we have three basic sort of fundamental relationships that we look at. The first is the intersection. And an intersection is simple. It's just where the one thing occupies at least some of the same space as the other thing. In other words, the road crosses the polygon, or the two polygons have a coincident boundary. In other words, a single boundary that is part of both polygons. The other thing we look at is containment. Is something inside of something else? Is the road inside the polygon? Is the little polygon inside the big polygon? And then proximity. How far is thing A from thing B? Seems pretty straightforward, seems pretty simple, and it really is. But to be able to deal with this in a geospatial way, in a software format, to use these conditions to extract information from larger data sets is really important. Lots of different spatial operators, spatial queries can employ a number of these. Here is just a short list of some of them. There's more. Let's take a look at a couple of these. Operators test relationships between two layers at a time. So they have a target layer and a source layer, and the textbook goes on and on and on about this. The target layer is the one the target layer is the one containing the features to be selected. The source is the one containing the features to be compared to. That's how they explain it. Probably in 2 or 3 slides or another chapter they'll change the daggone explanation again. So don't get too excited if these definitions of source and target get a little confusing sometimes. So with the various intersection operators, features intersect when any part of one feature touches, crosses, or overlaps another. And there are special cases. And there's lots of those lists, and you can go through everything from are identical to the boundary of a shared line segment to are crossed by the outline of their centroids to Clementini. Clementini is a really weird one, and we may talk about it more in a bit. But when we look at these contain operators, features that enclose all of another feature are said to contain it. Within is the inverse of contain. That really doesn't make sense to me. Anyway, different types of containment. Contains, one feature lies inside another. So for example, Oregon contains Columbia County. Completely contains, that's when one feature lies inside another and it doesn't touch the outside boundary. See, Oregon does not completely contain Columbia County because the border of Columbia County is also the border for the next state. Within this, the inverse of contains, Columbia County is within Oregon. Jefferson County is completely within Oregon. If that makes sense. Eliseo Clementini and his co-authors come up with a special set of topological relationships concerning containment. Clementini considers the boundary of a polygon to be separate from its inside or its outside. The Clementini operator is equivalent to the standard operator, except the source feature only lies on the source feature lies only on the boundary of the target feature. So an example of Clementini, the Rio Grande River lies on the border of Texas. So the contains operator would select the Rio Grande, the Clementini contains would not, because it considers that the Rio Grande is the boundary and it's not part of Texas. It simply is the boundary. Proximity operators, they test whether something is within a specified distance of something else. Volcanoes within a distance of interstate, for example. Additional examples of proximity: counties that are closest to state capitals, counties within 200 miles of a city, select counties that intersect rivers, or select rivers that intersect Texas. And you can see how basically these rivers run through many counties, and so you can identify them that way. Or you can do like the select rivers that intersect Texas, and so only rivers that cross Texas would show up. Cities that are within 20 miles of an interstate, cities that are within counties named Washington. These are all just different examples of containment or proximity. Scale and accuracy actually becomes an issue with spatial joins. It becomes more paramount than what you might imagine. And it's not always just errors, it's actually just the scale of things. Remember that a lot of features are generalized. And what does that mean? It means that, as I'm fond of telling my students, the world is a really big place. And there's a whole lot of it. And we can't put it all in all its detail and splendor in the GIS. At some location, at some scale or resolution, we're going to have to lose detail because we just can't do it. And so here we have a river or a road, I can't tell. And whatever it is, it's an important boundary between the stuff on the right and the stuff on the left. Now, we generalize where that exists with the blue line. If we were to zoom out further to a different scale, say 1 to 100,000, that river may very well look like that blue line. We get into 1 to 24,000 or 1 to 5,000, it's not going to line up perfectly. Why does that matter? What if that line is the border between the two counties, and the border between the two counties is actually the river? All right? There are places that would be in the wrong county that are on the right side, the opposite side of the river, and so when you try to locate where points are, you could mistakenly identify something as being in the wrong place. Topology issues. The real world, certain boundaries coincide. This doesn't always hold true in a GIS because we draw one thing and then we draw the other thing, and where the two things should line up, they don't. Now, in a perfect world, we set up our various rules of topology and we use our various tools when we're editing and drawing and creating things so that we don't end up with situations like that. But in reality, you might be working with multiple data sets that multiple people put together or working together on a project, and you end up with something like this. Here we have South Dakota and Nebraska border. We have Shannon and Bennett County borders, and we have the Pine Ridge Indian Reservation. Now, all of eastern and southeastern Shannon County is the Pine Ridge Indian Reservation. The reservation ends at the county line. The county line also signifies the southern border of South Dakota. So that also makes it the northern border of Nebraska. And Bennett County is what happens as soon as you drive out of Shannon County. So they all should line up. And yet, the Pine Ridge Indian Reservation does not line up with the boundaries of Shannon County, Bennett County, and the North Dakota, Nebraska, or South Dakota, Nebraska line. This is an issue of topology. Other extraction functions that are very similar to select by location, but what makes extraction functions useful is they split features that cross boundaries. And so the first two we're going to talk about is clip and erase. Clip extracts features within the boundary. Erase keeps features outside of the boundary. So when they're talking about boundary, I like to think of it as a cookie cutter. And when we talk about the feature, it's the cookie dough. So if we look at this set of images, looking at the top row of images, the box with the X is our cookie dough. The double circles is our cookie cutter. And if you were to imagine taking that cookie cutter and putting it on top of that cookie dough and pressing down, the cookie would look like the thing on the right. That is clip. You take the one thing and use it to cut that part out of the other one, and you keep the part you cut out. Erase is sort of the opposite. Same idea, cookie dough, cookie cutter, but instead of keeping the cookie, we keep the rest of the cookie dough. Um, extract extract functions extract portions of features based on an overlay layer. So basically, you have one data set, you take the other data set, you say, okay, I want everything that's inside this. So you clip it, and you get a new data set made up of just the parts of the old other data set that would fall inside your clipping data set. Or you could do erase, where it would give you a new data set minus all that space. And that's how you would use it. The clip and erase functions ignore all the internal boundaries and attributes. In the clip layer, the entire region is used like it's a simple cookie cutter to extract features from the input. The attributes of the input layer are simply brought through unchanged. So if a road was 50 miles long and a mile of it came inside there, that road's still going to be listed as 50 miles long. That's why length and area changes are important, because when you clip functions or erase functions, when you apply clip or erase functions to features and it modifies the geometry of things, those area and length fields are not always automatically updated. Now, it's important. Geodatabase feature classes. All right, feature class in a geodatabase. They have a field called shape_length and shape_area. Those two fields are automatically updated. Any other length or area based output fields are not. Okay. I also want to reiterate, if you're not working with a feature class in the geodatabase, what if you have a shapefile? That shapefile, those fields will not be updated. I think it's always just best to assume that those fields are wrong, and after you make something like this, or after you change a projection on the data, or any of these sorts of things, to where you have messed around with the shape in any fashion, you should update the geometry to make sure that those measurements are correct. I just always assume they're wrong. On-the-fly clipping is a temporary clip applied to a map layout. It does not create new layers or affect lengths or areas of the sources. It can be performed on many areas simultaneously. It can be removed when you don't need it, and it can be set as a data frame property. And so think of it as a way of just making a quick and fast temporary looking clip without actually clipping anything. So here is how that kind of works, clipping data with data frame layers. You go into data frame, clip options, specify the shape, select all that stuff, and then simply follow through.